Okay, so we are here for the third and last day of the mini course from Sinai. I hope we do not fall off the back of the doggy right now. So yeah, we can go.
Can you, now it's okay? Okay, thank you. Yeah, so thanks, Kayo, again for the invitation and the rest of the organizers. Thank you. It's been very good. And today I'll give you a homework problem, but it's the last day, so you don't have to submit your solutions. So it'll be a friendly homework problem. But so let's start where we left off. So we left off with some new results. I should remind you, let's see, so yeah, so maybe I should remind you using an example. So suppose we have a triangle, and I'm going to use, let's take a rational triangle. So let's be as simple as possible, and we'll say it's, let's say the vertices are 1 over a0 and 0, 1 over b, where a and b are integers, and even co-prime. So you notice I'm starting very slowly because I'm waking up as well. So, so these are integers, so these are rational numbers. And here's a triangle, let's call this P. And we said we're going to look at TP, which is the dilate. And then we'll look at the integer points in TP. So TP is, you know, you dilate it. So this is T over A and T over B. And we count the integer points. So if you count all the integer points, how many there are, it starts being number theoretic and so on, and it's related to topology, geometry, Fourier analysis, kind of dynamical systems now we see as well, but simple dynamical systems, a very simple dynamical system. But I challenge you to find the period of that dynamical system. It seems simple, but I bet you will not be able to find the period. So we'll see. Let's see. Or maybe you will, but I will be surprised because it seems like a challenging, yeah, it's a challenging problem. All right, so this is a polynomial, and so Earhart proved that the leading coefficient is always the area. That's easy. There's a certain quasi-linear term and a quasi-constant term. So these are periodic coefficients of T, periodic. And we said we're going to let T be any positive real now. So as T grows, you have a periodicity. And for many years, we didn't have any explicit expressions since the 1960s, I guess for 60 years. But now we have some explicit expressions. So, so let me remind you again. So I guess this is from 2026, that this is so you sum over the vertices, and you have summation k equals 0 to d, d choose k, the Barnes polynomials, and then you have these discrete moments. And so these discrete moments are finite sums over a lattice flow on a torus. So And when we say modulo the fundamental parallelepiped of the vertex tangent cone, it's really what we mean is that it's the same thing as saying that really, if you like, P is in the lattice flow. So you let the lattice flow with T in this direction, the direction of V, the vertex, and it's the same thing as just intersecting, really. So if it's the same thing as intersecting, why do I just not write that? Because this is more suggestive of number theory, just mod P, like you work mod P, you work mod the fundamental parallelepiped. And in number theory, you don't usually think in number theory mod P. If you work mod P or modulo N, you don't usually think of this parallelepiped, but you really are working mod a parallelepiped. It just so happens it's a one-dimensional parallelepiped, and it's closed and it's open here because N is congruent to 0. So as soon as you move here, you go back here, and so you're on a circle, right? So in one dimension you're on a circle, you're working mod N, and the same thing is here. It's there's a fundamental. It's traditional to use capital pi. So you're working modulo a one-dimensional fundamental parallelepiped as well. So just kind of using the ideas of elementary number theory, we might as well abstract to higher dimensions and work modulo a parallelepiped. And it's an integer parallelepiped, so it does have number theory, in fact. In fact, it's not obvious, but these things contain Dedekind sums. They generalize, so Dedekind sums are a big branch of number theory, and it turns out it's not obvious, and I don't know if I don't have time to go into it, but these generalize and extend the classical Dedekind sums, the Fourier Dedekind sums, the Zagier Dedekind sums, and other Dedekind sums. So everything is kind of contained in this in a kind of a hidden way. Okay, and these are the Barnes polynomials. And so there's no periodicity here. These are just polynomials in several variables. So all the periodicity is contained in the discrete moments. Okay, so far so good. Now, there's so many things we can do. Let me mention the work of Eva Link. She's kind of a genius. So there's a theorem by Eva Link, 2011, where she proved the following thing. She proved that these coefficients for any rational polytope in any dimension, they satisfy a certain differential equation. So one of her results is that if you consider this general quasi-polynomial like we have here, so for let P be any rational polytope. So again, the coordinates of the vertices are any rational points. And you consider by definition, I'll just remind you over and over again, this is you dilate by the object by T and you count. And so then what she proved is that d by dt of CR, the rth coefficient, so these are now these are periodic functions of T, and they can be kind of strange. She also proved that for the first time in complete generality, she proved that they're piecewise polynomial functions. So she proved many things. In a very short, brilliant paper, like 10 pages, she kind of just generalized the whole theory, and she proved that this is equal to minus, let's see, what was it? Minus r times c r plus 1 of t. So it's kind of a very simple differential equation, but very surprising. It was the first time that anybody proved that there was a differential equation. I think it's r plus 1, sorry. So this is one of her results. She also proved, yeah, that these are piecewise polynomial in general, and that they satisfy this differential equation for all the relevant t. So you don't look at t where you have a discontinuity, obviously. So for all the t's where you don't have a discontinuity, you have this. And so, yeah, and also for the first time, she considered all t. So she considered all positive t. Yeah.
So this CRT for all r meaning that it's piecewise, but also you interpolate here.
Yeah. So it's for all t where the t stays away from the jumps.
Okay. So like the discontinuity points, they transfer from one periodic function to the other.
Yeah. So we won't consider the points where it's jumps, yeah, the discontinuities. We do not consider discontinuities. But the discontinuities, there are finally many of them, so. Yeah, so it was very interesting, and so everybody got excited about this, me too, because we thought, wow, this is new, and this is, yeah, for the first time it appeared in 2011, and maybe we can get some kind of formulas for the coefficients now, because we have a differential equation, and look how simple it is. And it kind of lay undiscovered for, you know, forever until 2011. And yeah, so she was a PhD student of a friend of mine in Berlin, Martin Henk. And then Martin told me that she left mathematics. And I was so sad. I never met her, actually. And I was so sad that somebody so brilliant would leave mathematics. So don't let that happen to you. She might still come back. Who knows? So yeah, so maybe she's making billions of dollars. Who knows? I don't know. But yeah, so I wanted to show you now a new proof of this. So this follows now immediately from these explicit formulas. It's not so surprising because now we have explicit formulas. So this follows immediately. Eva had to work much harder because there are no explicit formulas. But her proof is kind of, I would say, more brilliant than mine because she had to actually work to get these things. Once you have these explicit formulas, everything follows quickly now. But I recommend her paper because it has some very interesting ideas that we can still use. All right, so far so good? So let's see how Eva's differential equation, it's an ordinary differential equation because it's just one variable t, the dilation parameter. So let's prove her differential equation. So I guess before the proof, I guess I should say this part B of the theorem. So this theorem, let's call it part A that I just wrote down. Part B is that C, the coefficient, we can give closed forms for the coefficients as well. And let me write that down. Let's see. Is everybody still on the back of the dog? Yeah, okay. Questions? Okay. So CR of t, the same CR as the periodic coefficient of the quasi-polynomial is, let's see what it is. So it's, you sum over the vertices. You always have to sum over the vertices, of course. And then you have the inner product of the vertex to the R. And then you have a finite sum, d minus R. Now, everybody's familiar with multinomial notation. So if, just a usual multinomial notation. So d factorial divided by j factorial divided by r factorial divided by d minus j minus r factorial. There are 3 factorials in the denominator, and then these are the Barnes numbers. So Barnes numbers, which generalize the Bernoulli numbers we talked about last time. I'll remind you what the definition is. You take the Barnes polynomial and just evaluate at 0. So it's the constant, this is the constant term in t, so there's no t's anymore. But the coefficients, as we said last time, are rational functions in the coordinates of this vector. So the coefficients are homogeneous rational functions in the coordinates, but there's no t anymore. And so it's a bit of a mess, I know, but it's an explicit mess. So this is the same discrete moments of the parallelepipeds. Yeah, so that's the explicit description of the rth coefficient. And then we could just, to check Ava's theorem, we just take d by dt of this now. And when you take d by dt, there's no t here, there's no t here, there's no t here. The only t that appears is in the discrete moments, which João would claim is a trivial dynamical system, but it is a simple dynamical system. It's probably one of the simplest there is, but unfortunately we're summing these polynomials over it, and that makes things much harder. So the period, you might think that the period is the least common multiple of the denominators. In general you'd be right, but infinitely often you'd be wrong. So it's in general it's not. Sometimes it is, kind of. So I'll show you, yeah, we'll go through a quick proof why the least common multiple is a period, but in general it's not the least, it's not the smallest period because of you summing these polynomials, and these can interact with this in a weird way that we don't understand yet. So yeah, the dynamical system is very easy, but you're summing these polynomials and it makes things very tricky. Okay, so when you do this, all you have to do is differentiate with respect to the flow, to the lattice flow. So all you have to do is notice that you can write these, now I'm calling them polytope Dedekind sums because they generalize all the Dedekind sums that I know, but they're also discrete moments located at the parallelepipeds and at v vertex. But so if I use the word polytope Dedekind sum, just think discrete moments. So we take this polytope Dedekind sum and we rewrite it. Let's rewrite it as follows. So you take this flow. Let's massage this flow a little bit. So it's the same thing as we said, as taking the intersection with the half-open parallelepiped. And now let's rewrite it as, let's put the t times the vector v on the other side and make a change of variable. So it's pi v plus t v. Oh, sorry. If we make a change of this change of variable, if you let p be something q, so q belongs to the lattice. So q belongs to the lattice, and you're moving. So it's easy to visualize, right? Instead of moving the lattice, you fix the lattice, and now you move your object. And so we move our object, we move q by minus tv. This is z. It's still a polynomial. Now it's a polynomial obviously in t as well. It's kind of a nasty polynomial, but it's a polynomial. We can make it even more explicit. We can write this polynomial as the q inner product z minus t V inner product Z to the K. And now it's clear, it's even clearer that it's a polynomial in T, but because of this, it has some, not singularities, but jumps, discontinuities. So every time the T goes a little farther away, you want to go back modulo. So it has these discontinuities. Never mind where discontinuities are right now, but it's clear that it's a piecewise polynomial in T. Again, one of her theorems. So it's a piecewise polynomial in T. Now it becomes obvious why it's a piecewise polynomial in T, and moreover, you can differentiate now with respect to T as long as T doesn't hit the boundary. So let's stay away from the boundary of the parallelepiped. As long as this is not in the boundary, you can differentiate with respect to T wherever it's continuous. And so the derivative, it's obvious, you just take the K down, and this K becomes D minus R minus J. An extra V dot Z comes out by the chain rule. That extra V dot Z gets added here, so the R bounces to R plus 1, and you can see the R plus 1 in her differential equation here. So that's where the R plus 1 comes from. The V dot Z goes from R to R plus 1, and so I'll say after one messy step, you get Ava's differential equation. Is that okay? Let me skip this messy step, but you can see using this how the messy step will go. I just don't want to spend another 10 minutes with the messy step. So far, so good? Yeah, so it's kind of interesting. Honestly, I don't know what to do now with this differential equation, except it's very pretty. We should be able to do some more stuff with it, but I'm not sure what. But I think there are applications. None of us have thought of them yet. Exactly, very good. Yeah, I was going to mention it. Yeah, exactly. Yeah, good point. It's similar to the Bernoulli differential equation. And yeah, way back. In fact, when reading her paper in 2012, I saw her paper in 2012. Like shortly after she published it, I was wondering the same thing. There must be a connection, and now we see the connections to Bernoulli and Barnes. And yeah, maybe if Ava comes back to mathematics, she can tell us some applications of this. But so far, it's kind of a very pretty, beautiful differential equation. But I'm sure it'll have applications. Okay. So far, so good. Okay, so let's go on to the interior. Okay, so once you have a, oh yeah, this was fun yesterday. I think see, we were thinking outside the box, literally. I only thought of that afterwards. So open polytopes. So far we talked about closed polytopes. So if you have the open polytopes, you take away the boundary. So you're not allowed to have points on the boundary, and you just want to count the points in the interior. Magically, so there's a theorem due again to Earhart. And it's sometimes in the 1960s, but I think this one is in the late 60s. It took him another 10 years almost to prove it. It's a very strange theorem. It's called Earhart reciprocity. Now it's called Earhart reciprocity. And it says, so let P0 be the interior of P. So again, you just delete the boundary. Then you compute the usual number of points in the closed P first. So the usual thing that we've been talking about, you compute this, so the number of points in the closed polytope. you replace t by minus t formally in the polynomial or the quasi-polynomial, and magically you get the number of points in the interior. So if you want the number of points in the interior, just compute the number of points in the closure, replace t by minus t, you're done. So it feels like cheating, and the first time you see it, it feels false, but in fact it's always true for any integer, for any rational polytope in any dimension. And Ehrhart conjectured this at first. Actually, the first proof was not by him, it was by this famous mathematician called MacDonald. You may have heard of MacDonald, Ian MacDonald, Commutative Algebra book, famous book. No? Ian MacDonald, poor guy. He did so much stuff, you don't know. Anyway, so Ian MacDonald gave the first proof, I think, but then Ehrhart gave other proofs, and by now we have like 20 proofs of this. Let me give you the 21st proof using these closed forms. Now it becomes obvious. The proofs are not easy. This will be a trivial proof because we also have a formula for open polytopes. I erased the formula, so let me write the formula for open polytopes. And then this becomes an easy corollary. So I'll write it here. So I guess let P0 be the interior. Well, you already know P0 is the interior. Okay, I'll write it again. Let P0 be the interior of a polytope P. And by definition, a polytope is always closed. So this is the interior. Then the so the number of points in the interior. So by definition, it's the number of points in the dilate of the interior is this kind of it's kind of fun to think about this. So I'll write it again. So now you know all the elements, but all you have to do is replace t by minus t. And so this is the vector of linear forms. This is a generic z. Oh, by the way, all these formulas, z is a generic z, some generic z. And magically, the z's cancel here because this is just an integer. And so, and here are the discrete sums. So I wanted to, this is the interesting part. This is always the interesting part. This dynamical system, or just call it the lattice flow if you like. Now you just replace t, it was a minus t for the closed polytope, and it's a plus t for the open polytope. So geometrically, it's very pretty. The flow is now moving backwards in time. If you think of t as time, instead of moving in that direction, all you have to do is move in the opposite direction. You're kind of moving backwards in time, and magically you get the interior. It's kind of weird. It's strange. It's still strange to me to think about it, but that's what it is. Eventually, we'll get used to it, I suppose. So that's the, yeah, so you're moving back, so kind of backwards in the flow. So you're flowing backwards. The lattice is flowing backwards, and then you get the interior. So far, so good? Yeah, weird, but it's what it is. I'm not going to argue with nature. Yeah, so let's see. There are lots of things that we can do, and I had to make a choice of which direction to go. Let me point out some easy things. Everybody still in the back of the dog? Okay. So let me point out some very easy things, and then some things that we don't understand. Maybe I already mentioned it. So the very easy thing, for example, is k equals 0. So you have mu sub 0. So this by definition, yeah, so I guess I should, let me define this to be mu sub k of the half-open parallelepiped pi sub v, and then z is the parameter, and then t times v. I decided to use this notation recently because it has all these parameters, and we need all the parameters to capture. We need v, we need t, we need z, and we need k. So there's no, I don't think, if you think of an easier way, let me know to write it. But, and these are moments. I'm using mu for the classical moments. And so if you look at 0, this is just the sum of something to the 0 power. So you're summing 1 over the points in the lattice flow. And if you sum 1, you might guess what this is, at least. So anybody want to venture a guess? Well, as far as number of points, it's the number of points in, what's that? It's the volume. Right? So it's the number of integer points in in this guy, right? Because you think of this as a compact torus. And on the compact torus, the points are not going anywhere. They're neither created nor destroyed. They're just moving along the boundary of the compact torus. Right? So if you think of, right? So they're staying, you know, there's as many points for any t as there are for t equals 0. And the number of points for t equals 0 is just that. So it's invariant. The number of points is invariant. And so for k equals 0, it's easy. Interestingly, you're right to use the word volume. May I ask, why did you use the word volume?
It's not the regular volume, but like for each pointer, like some once, I can okay, you need.
Can you say it again? Sorry.
You have to normalize it.
Okay. Okay. Let's take a vote. I'm just curious, yeah. How many people think that the number of points in this, the integer points in this half-open parallelepiped is exactly the volume without any correction? How many people think there's a slight correction? Wow, okay. So everybody's wrong. It's exactly the volume with no correction. And don't worry, I was wrong once too when I looked at this for the first time. So it's a little strange, right? That it's exactly the volume. So this is going to be your homework. But let's check that. Let's do an example. Because it's weird, right, that it's exactly the volume. Usually this is false. It's almost always false for other objects. But let's look. Half-open parallelepipeds are very interesting. First, they tile space. And you can use the tiling argument to give you an asymptotic argument. Via an asymptotic argument, it becomes more reasonable. And in fact, that's one of the proofs. It follows quickly from these closed forms, but let's not go there because it's an overkill. Let's try to think about it. Well, let's do an example. Does anybody want to give us a half-open parallelepiped that's easy? So sorry? 1, 0, okay. So are you sure you want 1, 0? Okay. Okay, so 1, 0, I'll do. And something that's less trivial. 2, 1. So 2, 1. Well, that's not going to have any non-trivial integer points in it. 1, 1, 2. Okay, 1, 2, or even 1, 3. So here's 1, 3. We'll do something even. Here's 1, 3. This vertex. And so this parallelepiped, you have to do. This is going to be open. So this is open. This is open. Remember, the only thing that's closed is the origin. And now we have to consider all the integer points in the all the integer points in here, well, it's 1, 2, 3. And what's the area? The area is 3. We could do more complicated things. The surprising thing is that it works for anything in all dimensions, right? So that's your homework. So let's see. So let's do a slightly, if we do something like this, it looks a little bit weird. It looks a little bit. So let's look at maybe 3, 1. I use 3, 1, and 2. Actually, let's look at something that's not primitive. Nobody said it has to be. Well, yeah. Let's look at something that's not primitive. So 2, 4. 2, 4. So 1, 2 is on there. It's on the boundary. Now we have another one on the boundary. So here's 3. Let's see. So 2, 4, 1, 2. I have to be careful here. And so 2, 4 plus 3, 1. That's 5, 5. I guess. Is that right? And if I'm doing it correctly, I should make sure that I catch all the points. So now the points are 1, 2, 3, 4, 5, 6, 7, 8. If I did it, 9. This is open, always, by definition, and this is open, and this is open, and this is closed. So did I catch all the points? 4, 4. I missed 4, 4. Is it in there? Actually, it's not clear if it's in there or not. Sorry, I didn't. It's in there? It's over or under?
On the diagonal.
Oh, it's on the diagonal?
Yeah, on the diagonal 0, 0, 5, 5. So.
Oh, it's on this diagonal.
Yeah.
Oh, so it's here. Oh, sorry. Oh, yeah, you're right. Sorry, you're right. You're right. Good point. Good. All right. Yeah. So, yeah. So, yeah. It's not. Yeah. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 if we did the arithmetic correctly. And now you know how to compute you just take the determinant of the matrix. That's also the area of the parallelepiped. So all you have to do is compute the determinant. And so it's 2 minus 12. Magic. So it's 10, right? So the area is 10, the number of points is 10, so it checks for 2 examples, therefore it's always true. Now, I say that as a joke, therefore it's always true, but we have to be careful. The more we use AI, the more you're going to believe that 2 examples they cause everything to be true. So be careful. We have to be careful. But yeah, so this seems to be exactly the classical volume. Surprising, right? But it's true. So the upshot, the conclusion is that for mu0 you get exactly the volume, which is cute, and it's also, it matches interestingly the classical moments. The classical moments of an object, the 0th moment is the volume classically. So luckily here it's the same. Even though it's discrete, it's a discrete moment, it matches with the continuous moment, in fact, because so some things match. The first moment should be the center of mass, and I can show you the formula. Yeah, sorry.
So that's similar to Fick's theorem.
It is. I was going to mention that exactly. Yeah.
Very similar.
It's similar, but Fick's theorem applies again to closed polygons, and so it doesn't quite follow from Fick's formula, but it's close. It's in that neighborhood. Yeah. So I should mention, everybody heard of Fick's formula? Okay, so I should mention that because it's kind of the classical two-dimensional result that a lot of this stuff generalizes Fick's formula from 2 dimensions to higher dimensions. Yeah, so the 0th moment is easy. The first moment is harder, but I found a formula for it about a month ago. It's a mess. I'm not going to write it down. It's a big mess, but it's a formula of some sort, and it relates to the center of mass. It's kind of a discretized center of mass formula. And then the higher moments are, well, these are the polytope sums, and you're summing over trivial dynamical systems, but the sum is a polynomial over a very easy dynamical system, so it becomes harder. But it's nice to see that there's some kind of extensions of the volume, but the kind of discretized extensions of some sort. To the bang? So, yeah, so see if you can prove this. I'm curious to see. I know of 2 different proofs. And I guess the 3rd proof would be very messy, but it doesn't follow from my formulas as they are, because my formulas hold for closed polytopes or open polytopes. And this is half open, so it's in between. But I'm writing a paper with André exactly for these things, actually. André's not here. Okay, let's talk about André. No. You know, he's a very cool guy. So, and he's a chess master. You know, essentially a chess master. So yeah, so these are very kind of pretty, and I thought that it's good to have like easy things as well as difficult things. Maybe I should, let me finish with one more thing. I should finish quickly, I think, right? Okay. Okay, so maybe I should talk a little bit about Dedekind sums, more classical number theory. But very, very, in one sense, it's advanced number theory. In another sense, well, it's classical, but it's still kind of advanced number theory. So I like the example we started with today, going to 1 over A0, going to 0, 1 over B, and looking at the dilates T. Let's stick with this example and compute the number of points using the theorem that we have. So using our theorem, or other theorems, you can, for this example, it's actually not too bad. The number of points, again, by definitely, it's again the number you dilate and you count. It's the area of the triangle. So this is kind of fun. It's the area of the triangle. What's the area of the triangle? 1/2 the base times the height. So it's 1 over 2ab times the t to the d. The d's is 2, plus a certain coefficient times t, plus a certain. So these are the periodic functions of t. Let's see what they are. This one is 1/2 1 over a plus 1 over b plus 1 over ab. It turns out to be the discrete kind of discrete surface area. Discrete surface area. Yeah. So what that means in this case is, if you fix let's fix any real t. I think t, in the formula I'm writing, t might have to be an integer. Okay. Okay, so let's fix an integer t. Then the number of points on the boundary, the number of integer points on the boundary divided by 2 turns out to be this. I think for this formula, yeah, I'm sorry, I wanted, in general, this is going to be a periodic function of t, but I think I wrote the formula for integer t. I apologize. But anyway, even for integer t, it's very interesting. So remember, we said that as you go down, the coefficients become harder and harder to compute because they capture more of the geometry, The next to last coefficient captures the graph, the one-dimensional graph, the edges of your object. And as we know, graph theory is difficult. And so the last coefficient, it should be, oh no, okay, it is. Maybe this is for all real t. If it's integer t, the constant term will be 1. This kind of weirds me out though, anyway. But now what is the coefficient C0 of t? So this coefficient, so I'm erasing because I need this whole board to write that coefficient, actually. So just preparing you for what's coming. So yeah, so this coefficient is 1/4 1 plus 1 over a plus 1 over b minus 1 over 12 times a over b plus b over a plus 1 over ab. That was the easy part. Now the hard part, k equals 0 to a minus 1 of the fractional part of k over a minus a half times the fractional part of b inverse, the modular inverse, we'll talk about this, over a minus a half. And we're not done yet, wait. And plus, there's another one that's symmetric. It's symmetric in a and b, obviously. So as you see from the geometry, whatever the formula is, it should be symmetric in a and b. So these are actually Bernoulli polynomials. This is the first periodic Bernoulli polynomial. And this is B inverse. B inverse times B is congruent to 1 mod A. It's the modular inverse of B. So it's an integer, the modular inverse of B mod A. This is the modular inverse of A mod B. They're different, of course. And finally, that's the periodic term. And we're just in 2 dimensions, right? So this is the easiest possible thing we can ever do. And when you go to 3 dimensions, it gets a little bit harder. Instead of having a short thing like this, it kind of goes on for a few lines. And as you can imagine, that's why nobody can compute dimension 10 or higher for integer polytopes. It becomes, this term will start going on pages and pages and pages and pages. The AI can do it, of course, even if it's 100 pages, but it becomes very, very slow. So what are these? Now, it turns out this looks like a mess, but actually they're very beautiful functions. And these functions naturally extend the GCD, the classical GCD that you know about. So you know about the GCD of 2 integers. These functions, this function here kind of magically extends the GCD. So I want to mention how a little bit, and that'll be the end. So these are multi-dimensional extensions of GCDs. But it's not obvious, right? When you look at this, it's a mess. Why does this extend to GCD? So I want to describe a little bit how. Tudo bem? Okay. But it's interesting that such a simple triangle will give you such a complicated count. And by the way, that's the simplest formula we know of. It doesn't get simpler than that. That's after all the simplifications you can possibly do. So that's the simplest possible way to count points in a triangle, but in a rational triangle. Rational triangles are hard in general. Integer triangles are easier. So Dedekind sums, and this is one of my favorite topics in number theory. They generalize the GCD. So Dedekind, this goes, this is by Dedekind, and that's around 1890s or he defined this around the 1890s or so, a long time ago. He said, consider the following sum. Whoops, sorry. I'll use R. R goes from 1 to k minus 1, and this is k. So you're summing over the finite cyclic group, just the simplest possible group, the cyclic group of order k. Well, R equals 0 is missing, I know, but so this is the first periodic Bernoulli polynomial, and then you put h r over k, you take the fractional part, subtract the half. So to remind you, the fractional part of x is x minus the integer part. It's just, I think everybody knows, but just to remind you, it's the fractional part of x. It's a periodic function of x, obviously, with period 1. So it's the simplest periodic function we know. And it's not obvious, but I don't have time to go to prove it, but I'll just tell you another corollary is that the theorem that I put up that I discovered recently, that theorem, if you massage it, you can show that all the formulas are functions of the periodic function. All of those formulas are, so this function forms kind of a basis for all of the formulas in all dimensions. That was known before, but now again it's obvious from these. So there's an amazing result that it's called so Dedekind reciprocity. So the law, Dedekind's law of reciprocity, that if you take S of hk plus S of kh, if you flip these, so remember this is modulo k, but this is modulo h, so they're completely different cyclic sums. This can have 1,000,000 terms, this can have 3 terms, or 2 or 1. So this is equal to 1 over 12 hk times h squared plus k squared minus 3 hk plus 1. So this is called the Dedekind's law of reciprocity of Dedekind sums, or just the Dedekind sum reciprocity. There's a beautiful little monograph by Grosswald and Rademacher where they devote the whole, it's a short book, maybe 80 to 100 pages, less than 100 pages, and they devote the whole book to giving 7 different proofs of this. It's a Karras monograph. If you get a chance to read the Karras monograph, they're usually very small, and they're usually written by world-class experts who spend their lifetime studying some subject, and they really want to show it to everybody and share with everybody. And so the Grosswald and Rademacher is such a book. It's beautiful. It's really beautifully written. Grosswald and Rademacher, the famous Rademacher, the famous Grosswald, and they gave 7 different proofs. And since everybody, there's many extensions to other number fields, this is kind of over the integers, but you extend to other number fields and so on. And right, so why this function is the one that appears in the rational triangle. Why does it extend to GCD? It's because of this reciprocity law, and it's because, think of this as this is periodic mod k, so this is a periodic function of h mod k, right? Because if you add to h any multiple of k, that multiple cancels and you get the same thing. So it's clearly periodic in the variable h modulo k, right? This is periodic in the variable k modulo h. And that's exactly what the GCD algorithm that we teach our freshmen, or even in high school, when you teach the Euclidean algorithm, right? The GCD, you do that. You reduce modulo something, and then that becomes a thing, and then you reduce modulo the other thing. And so you're really doing something like this when you do the Euclidean algorithm. So this is the Euclidean algorithm in disguise. The only thing is it's not completely trivial. Instead of something simple, there's this polynomial, but it's a Euclidean algorithm. Because you can reduce, if k is 1,000,000, and this is 3, you flip it, and then you reduce 1,000,000 modulo 3. So now the 1,000,000 modulo 3, that becomes 2 or 1, so it goes from 1,000,000 to just 1 term or 2 terms. And so it's exactly And how close is this to Gauss's law of quadratic reciprocity? It's very, very close. So you can derive Gauss's law of quadratic reciprocity, which usually takes 20 weeks or 10 weeks in an elementary number theory course. By the end of the semester, you prove Gauss's law, and you can prove Gauss's law. It follows from this in just a few lines. So this is very close to Gauss's law of quadratic reciprocity. Interestingly, even though it's close to Gauss's law of quadratic reciprocity, if you use the fact that LP of 0 is 1, and you plug in 0, you get that this constant term, this whole mess, you plug in 0 here for t, you get, it turns out, if you do the arithmetic, you get exactly this. So the classical law of reciprocity that's 100 and some years old follows trivially from the constant term of this triangle. This one. Pretty cool. So yeah, so with that, maybe I should, there's so many, yeah, so the homework problem, I've already got the homework problem, right? Proved that the, and then a more difficult problem, which I'm thinking about, is the periodicity. What is the period? What is really the period of this moment? So given any rational vector v, given a real number t, given an integer, half-open integer parallelepiped, what is the period of this? And z is generic. What is the smallest, what is the smallest period? It's clear, and you can convince yourself, I'll skip the proof. It's very, very trivial to prove that one period is the least common multiple of the denominators of v. You just write v as a vector, the least common multiple. It's pretty clear from the definition. It's a period. But what's the smallest period? So I don't know the answer to that yet. So maybe I should finish there. I think everybody's still on the back of the dog, right? I think so. Okay.
Anybody has any questions?
Sorry?
So these 3 days we're only talking about polytopes and, I mean, integer polytopes, rational polytopes. What happens? Can we try to extend this maybe to slightly nonlinear things?
Yeah, that's a very nice question. I can, but I didn't want to mention it. Yeah, but only slightly. I can only do it slightly. That's right. I like to. I got this question from people in Berlin when I gave a talk about not this topic, but before I discovered this, like 2 years ago in Berlin, about various tiling things, and somebody was kind of joking about, you know, going to arbitrary real things. So I like to think of it, if you think by analogy, if you use your bicycle to go from IME-USP to your apartment, that's like solving an integer polytope. And then if you use your car to go from IME-USP to Campinas or to Rio de Janeiro or to some nearby country, in your car, that's like going to a rational polytope. Going to a real polytope is jumping in a rocket ship from here to the moon. It's that much harder. And so almost nobody does it. Littlewood tried to do it. Littlewood and Ramanujan and Hardy, the three of them, Hardy, Littlewood, and Ramanujan, they published 3 papers on integer points in real triangles. In fact, real triangles with a right angle, like exactly like the one I wrote, but now they're real, instead of rational, they're real. And each of those papers are like, one was 50 pages long, one was 70 pages long, and very complicated. And those are just for real triangles with a right angle. And they realized that it's interesting, but I would love to do that, yeah. And to some extent you can. If you translate everything, the integer polytope, by a real vector, then you can certainly. Mm-hmm. Translates work. Beyond translates, we can do some other things. There are things called semi-algebraic polytopes in the literature about 10 years ago, where you move a facet parallel to itself. So imagine the polytope is some object where you blow air into it and you go, and it kind of goes like that. All the facets move independently with each other. You can do that. and they can move arbitrarily real numbers, arbitrarily real directions, as long as the combinatorial type is the same. So in combinatorics is something called a face poset. The partially ordered set of the faces, they form a poset, if you guys know about that, posets. And the face poset, or the lattice, in a different definition of the word lattice, it's a poset using some facts about the poset, the Mobius mu function of a poset, for example, that Giancarlo Rota wrote about. Anyway, so more classical combinatorics of posets, partially ordered sets, you can start doing some more things, but it's hard even for tiny perturbations in the real domain. It becomes very difficult. So for example, Hardy, Littlewood, and Ramanujan, when they published these 3 papers in 1911 and 1915, around there, more than 100 years ago, they worked really, really hard, and they were able to do something like, does everybody know about number fields? So a number field is a finite extension over the rationals, as a vector space over the rationals. For example, if Q adjoint square root of 2, or Q adjoint square root of 5, or Q adjoint the square root of minus 5, it's imaginary quadratic field. These are classical number fields. If you have a triangle, a right triangle with a real slope rather than, so even if you go to algebraic numbers and you have, let's say you have 1, 0, and here you get the square root of 5, 0 square root of 5. So even something as simple as this, so here the slope is like square root of 5. Already the analysis of this becomes infinitely harder than anything we've done. But they notice something very interesting, that if you look at the asymptotics, if you now look at the dilate of this triangle, and you count the number of points on just the hypotenuse, in fact, that oscillates. Those oscillations have like a main term, as in analytic number theory. There's a main term, and and the main term involves the class number. So there's a class number of Q adjoint square root of 5. This is so the class number is already located in the main term of the oscillations, and then the other terms are much harder than the class number. The class number measures how far away from the unique factorization you are in the number field. So yeah, so already this is very hard, and they kind of did that, they noticed this. But if you go beyond algebraic numbers, then it's almost hopeless. But even algebraic numbers would be great, I agree.
And like for these algebraic numbers, you can try, is there a way to extend some like Brion theorem or that reciprocity result, something like this?
I have no idea. I mean, that would be great. I think some things, yes, can be extended, but only a little bit. I don't know how to extend it fully. If you discover it, let us know. Definitely. Yeah, I don't know how to do that. Yeah, but that would be fantastic. Yeah, very nice question. Yeah.
So, if not, let's take.
Okay, thank you. Okay.
So now it's over. Thank you very much, Sinai.